Hi everyone, welcome to the Data Idols Summer School and welcome back to our community who have been following us for the past 5 years. I'm Courtney and I'm a recruiter here at Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months so you can learn in real time and pick up new skills from the comfort of your home. These sessions are ideal for people transitioning into data or for those starting their career. Please use the Slack channel if you're watching this session live to chat with other attendees. The link will be in the chat soon. Thank you to all our partners who made this event a success and for the 400 plus hours it took our team to make this summer school a reality. All sessions are pre-recorded and can be watched back at a later date starting in September. We will be emailing you with a link to watch the sessions back September the 1st and they'll be free to watch. So if you miss anything or want to learn your own pace, it will be available at this time. Today, our session is an introduction to Python libraries and algorithms for machine learning with Luke from Veolia. Thank you for supporting the Data Science Festival in partnership with Data Idols and enjoy the session.
Hi, and thank you for attending this talk on Introduction to Python Libraries and Algorithms for Machine Learning. I am Luke, I'm one of the data scientists at Veolia, and I'm just going to give you a brief introduction to the timeline of machine learning, the libraries that you use in Python to do so, and also delve a little bit into the algorithms. So without further ado, this is what we're going to go through. So I mentioned the timeline. We're going to start with that. We're going to go through the processing libraries, also talk about Pandas, formatting data for machine learning, and model training. And I'm going to do some demos in between so that it has a sort of hands-on element to it. So let's start. So timeline for machine learning solutions. So this is generally the pipeline or timeline that it normally goes through. So normally you always start with examining the data. So this can come in many formats. So sometimes it's in the data's in Excel spreadsheets, though a lot of people have moved away from that. Quite often it's in CSV files, and quite often it's also in something called Parquet files, which I won't go into too much on this talk, but it is definitely a format that's around. You also quite often get multiple files and you have to join them together on certain keys, and these are joining files. And alongside this, you also have to look at the data itself. And that's where cleaning the data comes in. So these steps are sort of hand in hand because you have to sort of examine the data before you can clean it, but they're quite closely related. So when you examine the data and look at the data, you might find that quite often you'll experience sudden spikes in the data, or where it would be a normal signal from some sort of diagnostic, and then it would shoot to like almost infinity, which is obviously a big error. And similarly, the signal might drop off to suddenly 0 and then back up to where it was again. It's stuff like this you have to actually look at the data itself to get an idea of that these bits are happening, and you have to work around that. And you also have to look at the actual rows and columns itself and see what's in them. So if you're very lucky, the data will look something like this, which is lovely and easy to use, but quite often it looks more like this, where you have to manipulate it and do some processing to make sure that it can actually be used. So we're going to go into that as well. So this all takes quite a lot of time, and I would say the majority of your time is actually spent doing this sort of thing. Running the models themselves don't normally take very long. So once you've got the data into a workable format, you have to do some further formatting to make sure that it's ready to pass to any machine learning model. And I'm going to talk about two things. So scaling data and getting data into categorical form for certain columns. So scaling data I'll talk about later, but it is how it sounds. You might want to scale the data between two values or between the mean and variance. And you also quite often have a lot of columns which are not numerical columns, they're categorical columns. So this could be a column that has a list of names in, places, text basically. And then you have to get it into a certain form if you want to pass this to a machine learning algorithm. So once you've done these steps, you're finally on to the point where you train the model. And then training the model is even that there's a few things you can do other than just train the model, but I won't go into them too much in this session. But you can do things like parameter tune, you can have a selection of models. There's other steps in the training model, feature selection, but in this course we're just going to have a look at simple training. And then, of course, if you train the model, you're going to have to test it to make sure that it works well. And the normal procedure is to set aside a little bit of data, which is used to test on. So it's data that the model hasn't seen at all. It's completely fresh, and you have to make sure that the accuracy of the model is well when it gets into contact with data it hasn't seen yet. There probably is another step here, which is the deployment step, which occurs if you're building an automated end-to-end solution on a cloud service. I would say most of the time they're built in this fashion on these days machine learning models, but it's probably beyond the scope of this project, or sorry, course, and I will just run through these steps. So data processing. So talking about these parts, the main library that you use for this, if you hadn't guessed, it is Pandas. Pandas is a data manipulation library. It interfaces into C, so it's very fast. It's got a wide range of functionality. It's quite easy to use. I would say it's normally the go-to for data manipulation. I think there are other libraries such as DAX, but I personally don't know any data scientists that uses it. Pandas is normally the one for Python. There is also a library called PySpark, which is very good for big data. If you have access to a Spark cluster, I would recommend using this. It's not normally used on a local computer. It's more if you have a huge amount of data that needs transformations on. There is actually something also called koalas, which tries to blend between the two. So it tries to recreate Pandas functionality and syntax on top of PySpark. However, it's not something that I'm going to go into in this course, but it is out there. So the other library for actual machine learning, which I'm going to talk about, is scikit-learn, which you might have heard about. It's generally just a big collection of functions for data processing. It contains many algorithms itself, and basically all you need to get started with machine learning in Python. Also, the syntax that it follows is, you'll find if you were to use other libraries, they tend to follow the same syntax or trend as scikit-learn, which I'll talk about later. So I'm going to talk about Pandas and walk you through kind of things it does. So I mentioned earlier about joining. files together. So you can do this in Pandas as well, where you might have two separate files and you might need to join them together to make the file that you pass. And this is done in Pandas with a function called merge. And you have different types of joins. So you have a left join, right join, inner join, and outer join. And I'll demonstrate this difference between the two, or difference between the four even, in a minute. And you also have to look at things when you're doing data science, like handling NaN values, so number, like blank columns basically, or blank entries. This is done, you can do it several ways. So you can drop out the rows completely. You can also fill them in with other values. So you can see these are the functions here that you use in Pandas to do so. We'll run through all this, but this is kind of things you look at with Pandas. You can also replace certain values, and in fact, that should be a blank column, but the idea is you can replace any value here with another value. So finally, also I'll talk about slicing. So slicing is a bit like filtering. So if you can pass a condition to Pandas data frame, and then it will filter basically only those values or any condition that you put in. And this is very useful if you want to process or replace strings only for a certain type or certain condition. So before I go on to this, I am just going to do a quick demo to show you how it works. So this is an IDE called Spider. This is very good for Python. I'd recommend it. There are others as well, such as things like PyCharm, etc. There's also VS Code, which people use. This is just one I'm going to use for demo, and it's one I'm used to. So I'm just going to very quickly import Pandas. So when you start a new script, you have to start by importing libraries. So you import Pandas like so. I like to import Pandas as PD. It's just sort of a shortcut. So you can put that over there. You can also import NumPy, which is another Python library, which I would definitely recommend. It's not strictly for data science or data manipulation, but it does go hand in hand with Pandas, as you'll see. I am just going to create a very quick data frame, which I'm going to use to demonstrate joining. Okay, so this is just a random data frame I'm creating, so you won't need to do this. This is just to show you how to do some joins. So I'm going to create a second data frame to join on now, and then we shall start. So if I go to Variable Explorer, I'll show you the data frames that we're joining. So this is just a demo data frame. So you have the names, age, height, and then have this column called average mode of transport. Now, say if you had another data frame where you wanted to join on average carbon footprint index. And you can see here there's there's a link between the mode of transport and this data frame here. So if you wanted to join this, you would do the following commands. So I mentioned merge. So if we go into the window and do pd.merge, and then there's the left and right data frame that you want to join. So the left data frame I want to join is the data, and the right one is the carbon data frame. So, and then you have to tell what index to join on. So you can do that through the command left on. Average mode of transport, and then you tell the right column to join on as well, which in this case is mode of transport. Right, with any luck, see, you can see here that it's joined the columns together here. So you can see that it's tallied them up. If I save this in another data frame so you can look what it's done. See here, it's matched up the columns, and now in that data frame you also have the average carbon footprint index, which is what we're aiming for. So I've also, so you can see here it has the left column and the right column we joined on, but really what we want is a single column. So because these columns are, so the mode of transport and the average mode of transport are basically the same column. So it makes sense to merge that into one column. So if you wanted to convert this to one column, you do carbon data equals rename, and then you tell you list the column that you want to rename. So this basically standardizes the columns so that they're the same. So now if I run this command, and now if you look at the carbon data, it's now got the same column heading average mode of transport as in the data file. So now that you've made that adjustment, the command now literally just changes to pd.merge data and then instead of doing the left on the right on, you can just join on the same column, which is a lot easier. You see, so now there's only one column, and it's gone from a data frame with 6 columns, sorry, to 5, which is much easier. So this type of join is actually inner join. So I said there's left and right joins. So I'll just show you what happens when you want a left join or a right join. So if you wanted to change the type of join, you use the command how equals, and then I am going to do a left join. Let's see how that shows up. So you can see here, there's something slightly different. So this data frame is now has 9 rows instead of 8. And that's because if I go to the original data frame here, you'll see that Fred's average mode of transport is unknown. And if I go to the carbon data frame, you'll see unknown isn't in the list here. So make sure that that entry isn't deleted, but it basically fills that entry with NaN. So that this is what a left join is. It makes sure that the data, all entries are accounted for in the data in this join, but it doesn't drop any out. If you wanted to do a right join, oops, you, as you would imagine, use how equals right. Now you can see that there's entries here that are now NaNs, and that is because if we go to the carbon data, there is an average mode of transport called horse, and most people don't travel by horse, but it's in this data set, so it includes horse as a possibility, but it doesn't join it on any actual name. So finally, the final join is outer, which includes everything, as you can see. So those are joins. Now I'm also going to talk about cleaning data. So one thing in Spider is you have to make sure at the top here that you navigate to the right directory. So I'm going to, this is something I've made already. So if I go to the path where my scripts are located, which are in here, I believe. Yes. So this is the correct path. So once you have the correct path and you import, start fresh in new script. So if we do import again, and as PD, import it. There is actually a command that I quite often do, which is PD dot set options. What this does is automatically increases the amount of columns to display on the IPython console. This is just for convenience, so you can see more columns. Otherwise, it will only show you a few select columns, and you want all of them to look at. So then once we've done that, we need the file that I am going to read in is this one called uncleaned. So if we pass that to the variable, it's now defined the name. So then if we want to import the data into a data frame, we use the following command. Like so. So if you notice, this is a CSV file, which is a comma separatable file. And this is quite common in data science. You normally get them in this format. So this is the command you use to read it in, and with any luck, it's read it in. You can see that it's read in this file. So this is the idea of the kind of things you might want to change. So if we look here, you can see that there's actually a blank entry there, and really that should be the same as these. It should be a NaN value, which is basically an empty cell, but it's not, and that is because it has a space in it. So one trick you can do with Pandas is, if I go back to the command I was looking at before, which is this one, and you can pass an argument called NaN values, and you can define values that it reads as an AN column. So if I put the space in and run the command again, you will see that it now actually recognizes it as a blank entry, a blank cell, which is what you want. Now, you need to handle these as well, because they are a real pain unless you handle them early on, and quite often it'll crash your scripts if you don't do something with these. So there is a pandas command called drop NA, which drops those columns. So the way to run it is to go data dot drop NA, like so, and you'll see it removes all the instances where you have these blank entries. Now, you might not always want to do this, because you can see it only leaves you with 2 rows if you drop everything. So if we go back to the data, you might only just want to drop this row here, which has a completely empty row. You might not want to drop these. So if you just wanted to drop a single row, you can go back to the command data drop NA, and then if you use the how equals all, it basically makes sure it drops rows where everything is blank, not just a single instance. So if we do it like that, you can see it keeps the rest of the columns. It only drops the bottom one, which is completely blank. There is also one final thing about drop NA I wanted to show you. So data drop NA, it's now you notice that every time I have to run this command every time to redo the actual dropping. So if you wanted to make this permanent, you could either pass this to a variable. So you could either do something like new data equals data, like that, and then this will be your new data frame. Or you can use a command called in place equals true, and what that does is it permanently changes the variable or the data frame data. So if I go there, it's now permanently changed it. So let's look at so what's the next thing we want to look at? So you can see in the age column, we have a 31 here, which of course we want that as integers. We don't want it as text. So when you have text, the normal command that you use to replace things like that is you type in the data frame name, you type in the column, which is age. So if you go .age, then the next step is to use a command called replace. So what this does is it replaces A with whatever different value you'd like. So if we type in 31, and now what we want to replace it with 31. Do that. Brilliant. It changes that column the way you want it. So now we have to make sure that that column is permanently changed by assigning data age to this operation we've just done. So if you do that, you now see that it's changed it to 31, which is good. And there you can also see there's a negative number here, which is the next thing we wanted to look at. So this sort of goes into slicing and filtering. So I mentioned that you can slice on with certain conditions or filter. So we could just do what we did before, which would just be to replace -1 with whatever value you like. But say if this was a very large data frame with lots of rows, and we couldn't just go through every single row, or for every time there was an age that was less than 0. So if we wanted to just do one command to filter all of these out and then set them to a certain value, you can do the data.lock brackets, and then you specify the condition next. Now the condition we want is every time that the age is less than 0, so when it's a negative number. So if we put data.age is less than 0 and filter, you'll see, so there is actually another step which I forgot to tell you guys about. So the reason it doesn't like this is because if I look at this column, it's an object column. Now an object column is basically a column full of strings. So we need to replace this with, we need to change the column type, and you can do that by data.age equals data.age, then use the command as type floats. Now we've done that, it will change the type, and we can go back to what we were doing before, and you can see now it filters out any column where the value is less than 0, because before it was that operation is not for string objects, it's only for integers or floats. So that's why we had to change it. So now we've found a way of filtering out instances where it's less than 1, but now of course we want to change those to a certain value. So with slicing, if you add a comma there and you specify the column that you want to look at, it slices first on the index and then on the column. So age is the column we want to slice beyond that. So now all you see is just the column. Now we want to give it a certain value. So this is where we use the equal sign to assign a certain value. Now we can pick any value. What I'm going to do is add the average value in that column. So you can do that by data.age.mean, and that will just give you the average value that is assigned to of that column, and it will assign it to any times where it's less than 0. So if we do that, and now if we look, there you have the average, and we no longer have negative numbers. And finally, I am going to show you about the country column. Now you can notice that there's not a space here, and there's also Greece not spelled correctly there. So we can do the string replace as we did before, but one thing I didn't mention is we can do data.country replace Greece, and then we want to change that to Greece. What I didn't mention is you can also add one on top of the other. So if you can, not only can you do that once, you could do this in a separate line, but you can actually add them on top of each other. So you can do a second replace, and this will work. So if we do United, change that to so now if you look, it does it, not only does it change the United Kingdom, it also changes Greece. So the final step is to make sure it's permanent by assigning this to the column. And there you have it. Right, so we've still got these blank entries here. So I said they can be a pain unless you do something about them. So the final command I'm going to talk about is fill NA. So fill NA basically just fills any blank entries with any certain number or string that you'd like. So if we go to data and we type dot fill NA, and then it will fill the entries with, let's put unknown. Do this. You can see now instead of blank entries, they have unknown. And let's also make this permanent by using the in place argument, which I talked about earlier. So you'll see later that quite often a lot of libraries and functions, they actually break if you don't fill these with certain values. So that's the reason why we want to fill them. So I've just replaced it with unknown. So if you look here, we now have a much cleaner and easier to use data frame, which can be used in Python libraries or machine learning libraries even. And you've done your very basic cleaning here. This is very basic. I mean, there's all sorts you can do to clean data. This is sort of just a very rough walkthrough. There's things like imputation, where you might want to, for blank entries, you can fill it with the average entry or mode in that column, or you can do more advanced stuff. You can do body matching as well. There's all sorts of things. But so this is a very basic outline of the kind of things you do to clean a data set. So let's go back to the talk. So now that we've done very basic cleaning, I'm going to talk about scikit-learn itself. So this is the go-to library that I mentioned earlier. So the way that the standard sort of procedure for scikit-learn is you import whatever functionality you want using this command, and then you pass the object to, you assign it to a variable and create an object, and then you pass any arguments you want. And then this is the bit that I want to emphasize. So this here, this is pretty much every single function in scikit-learn. They all pretty much follow this procedure. Not always, but the majority of them. Not only does scikit-learn follow this procedure, a lot of other libraries, like, so for example, there's an algorithm called XGBoost, which follows this sort of convention as well, and many others. So you fit, which means that you pass the data you want to perform the calculations on. And then once you've given it the data it needs to do all the calculations, you use the transform command here to actually transform the data or do whatever you want. And then fit transform is just sort of an amalgamation of both of them. So it just does one after the other. It's just sort of a shortcut routine. And yeah, you'll find that this comes up quite often. And even if you want to make your own functions, in scikit-learn, you have to follow this convention, which we're not going to do here, but you can do it. So I also mentioned about categorical formatting. So categorical formatting is when you have text like this and you want to arrange it in a way that a machine learning algorithm can understand it. And that's done via using libraries or functions such as one-hot encoder. There are others. This is just the one I'm going to run through. So what it does is it takes the names, it assigns it as a category, it gives it an ID, and then it shifts it into this format. So you can see John here, it has a 1, and all the rest are 0. And this is the way you pass categorical identities to any machine learning algorithm. So we'll probably do this in the actual training procedure, but you can do this before in any script, and you can see it follows, as I said, that procedure. So you create a variable, you pass in the arguments, and then you do fit transform to reduce it in this form. I also mentioned scaling, so you might want to scale the data. So there are a few ways of doing it. You can do min-max, but this one we're going to talk about is standard scaler. So standard scaler basically normalizes and centralizes it around the mean, and S is the standard deviation. So once you transform it, the data goes from this to this. This is fairly simple to do. To be honest, you don't always need to do this with every algorithm, but then there are some where you get much better results if you do. So, right, do I do a quick introduction, or do I do a quick demo of those commands, or do I do it in the regression part, this explanation? Tell you what, I'll do regression first, and then I'll do a demo. So the next step is, once you've got it into categorical form and you've trained everything, or sorry, you've got it into categorical form and you've done some scaling, the next step is to train the model. So there are a few different models depending on the problem that you want to look at. So sometimes you might want to look at regression, and sometimes you might want to look at things like classification. There's also things called clustering as well. So there's different types of machine learning, as I said. So supervised learning is the regression and classification, but there's also unsupervised learning, which is things like clustering. All that means is the supervised learning is you have to pass what entries are indicative of something. So for example, if you were looking at a load of data on difference between moths and butterflies, you'd have to tell it in the training data which entries represent butterflies and which represent moths. Whereas with unsupervised learning, you don't have to explicitly define what's what. It sort of does it autonomously. So the models we're going to look at is regression and classification today. So I'm going to do a bit of a quick run through of regression. Our apologies that there is going to be some maths here, and if you're not used to maths at all, then some of this might be a little over your heads. But what I would suggest is, if it is, go back and look over the things I'm going to talk about and see if you can get your head around it. But I would imagine most people have sort of come across some of this before, but I'll just run through it. So what is regression? So regression it's almost like a way of mapping data onto a function. So you have loads of data points, and you can have a function which represents all those data points through, in the case of linear regression, a line. So we can put a line through these data points, and it's represented as a straight line. So you can see it roughly follows this trend, and it roughly follows this line. So this can be used. It's a very powerful tool for making models to estimate certain predictions and forecasts, etc., providing the data's correlated well. So I don't know if you remember from school. So the equation for a line from school was line y, say, equals mx plus c. And it's the same here. I've just replaced the coefficients with betas. So beta naught is like the intercept, the baseline, and then beta 1 is the gradient of the line. And with those two values, you can draw a straight line through these data if you have those values. But there is also this error term here. So even if you have a line which represents the data extremely well, you're always going to get a little variation or deviation away from this line with the data points. And the idea is you want to minimize this error. So you can see here, there's this little error epsilon here, which is just this space here, but it's for all the data points. So bearing that in mind, the next step is we want to find an expression which can describe all these points but relates back to the line. And the way you do that is if you look at this one, for example, this data point, you can represent that if you have the independent variable x1, you can represent it as y1 equals beta naught plus the gradient of the line plus the error term, which will be here. And now with this, you can represent every single point, but it relates to this line, which is very convenient. And I'll explain why you want to do that. Also, X and Y is a bit of a boring thing to look at. I'm going to change this. So you wouldn't normally, if you were a data scientist, you wouldn't be given, I want to find out the correlation between Y and X. You'd be given something more like looking at the probability of having gray hair with respect to age. So, I mean, this is very obvious, but the older you get, the more likely you are to have gray hair. But there might also be other features or other things that impact grey hair. So you could have, say, something like a health index or a stress index, or I don't know, something like gender, ethnicity. All these sort of things could impact grey hair. So this is the next step when you want to look at multiple different features. So previously, this was a one-dimensional case where you have the X and Y axis, so that's one feature, but then you might want to extend it to multiple features, and this is where the real power of linear regression comes in. So let's just replace the numbers with these symbols. So if we take it to be this form, and let's bring in the equation we had previously. So y equals b naught plus beta 1 x1 plus this error term. So I said that was for the 1D case. We can extend it actually like this. So k is the number of features. So now what we have is, let me move this. So what we have now is a term for k amount of features. But we can go beyond this. This can actually extend whereby we put it in matrix form. So now we take this whole data set and we can express it as a matrix, which if you haven't done matrices before, which I'm sure many of you have, but I would suggest looking at matrices. They're basically a way of capturing a set of equations that are related to each other in this sort of box format, and they have certain properties, and they're very useful and they're very powerful. So n, it's basically the list here. So n is the number of samples and k is the number of features. So now you have the expression, basically the expression for a line for every single data point expressed like this. If we do some quick manipulation where we bring the error to this side, you can have the error as y minus x dot b. Now this is very useful because now we have a formula for expressing all the errors in this data set. So we have these two handy expressions. Now we basically, the next step is to find out what the coefficients are, because using these two equations. So going back to the line relationship. So you have these errors here between the data points, and you have the line that goes through them. And of course, you can have many different lines. This is just one of them. The line could go slightly up, go slightly down, it could be a completely flat line, and they would all have very different varying sorts of errors going along it. So what we want to do is we need a way of expressing how good that line is through a single value. And the way to do that is to use something called the sum of squared errors. So all that is it takes each of these error distances from the line, and it squares them and it sums them up. So the reason you want to square them is, let's take these two, for example. If these terms weren't squared, they'd cancel each other out, and they're quite big errors. So, but if you do square them, they add on top of each other, so it accounts for it. So you want to square it so you don't cancel out the errors that are above the line and the errors that are below the line. And then when you add them, you get a single value which represents how good that line fits all that data. You can see here that as you move the line up or down, there's the distance of errors between the lines change, and effectively it changed is this value. So what you want to do is find a way, you want to find the perfect sort of coefficients which give you the minimum value here, the best fit you can get through jigging around the coefficients. So how do you do that? Well, there's in a lot of scenarios here with machine learning, there's a minimum, and you want to find the minimum. So if you have those data points and you put the line into low, you'll get a high SSE value. If you put it too high, you'll go past all the data points and you'll have a very high SSE value. You want to find the sweet spot in the middle, which matches up perfectly. And you can see this nice well shape. This is a typical minimization problem. So if you remember from school, if you have a bottom like this and you have the well and you want to find what the minimum is here, if you take the differential and it is 0, that is the point where you're at a local minima. And once more, if you take the second differential, if it's bigger than 0, it's a minimum, not a maximum, because you can have it could either be a minimum or a maximum, but it can only be a minimum if the second differential is greater than 0. So we have these expressions, and this will tell us the point at which we're in a minima. So this is really handy because this makes the optimization problem very easy. So if we look at the term for the sum of squared errors and we plug in what we had previously with those expressions, you now have it in this format. And again, this might be where I lose few people through matrix manipulation. If you've never encountered it before, I'd highly suggest looking up matrices and stuff. Anyway, so you have this expression and you can expand it out to be in this format. And then you can finally take differential and equate it to 0 for where and then you get this expression. And then finally, just do your last bit of rejigging, and you get this lovely term here, which gives the equation for the coefficients. Now, that makes life very easy, because a lot of algorithms you have to do, define a step, run through a certain amount of steps, compare one step to the last, and then when the change is below a certain tolerance, then you can take it to be a certain minima. This is very simple. This is literally just plug in and play. So it's very fast and it's very effective. And you'll see it does actually work quite well in a lot of scenarios. And furthermore, if we do the second differential of this term, you will notice that you come out with this. And looking at it, you can see that it's not going to ever be less than or greater or less than 0, sorry, because remember, these are the samples, and you're basically squaring the terms in this expression. So even if you had negative terms in the sample data, because you're squaring it, you're not going to get 0 values. So you can safely say this is the local minima, which is good news. And if you also remember from school, in the one-dimensional case, it actually reduces to this, which is what you find in a lot of textbooks. So it's just basically a very handy way of expressing these formulas when you have multiple different features, which I think is pretty cool. So this is linear regression I've been talking about. So there are a few assumptions with linear regression. So as you'd imagine, variables follow a linear relationship. Each feature is linearly independent, and the data points are normally distributed along the y-axis for any given x. And there's little to no multi-collinearity, which basically means columns aren't very closely related. So an example, I can't at the moment, but it's basically to do with things like let's say, for example, the amount of smoke fumes produced a year by an individual and the amount of tobacco burnt every year by an individual. They're very closely related, even though they're different. They're probably different values. They'll probably scale almost perfectly. So that's sort of multi-collinearity. So I'm going to do a quick demo of regression just to run through it. So if we go back and we clear all this. Sorry, my computer's just restarting the console. So now it's done. Now, as we did before, do import pandas as PD. And also let's put in imports numpy as np. And also set the options. So let's display more columns as well in the console. So if we run these commands. Oh, by the way, for anyone using Spider, I don't know what it'll be like if you were using other IDEs, but if you use Shift and Enter on this, it will just run that segment like so. Okay, so let me check we are in the right directory. So file. No, we're not. So we need to change the directory. So if we navigate to the directory where the files are in, that's better. So we're in the right directory now. So now we need to define the file name. So for this demo, I'm using a file called sales regression train, which will define that. So put that in here, and then as before, we want to read in the data. So let's do that. So data equals read CSV. Let's look. So this is a data set which is available on the internet. So this is looking at item sales and comparing different features to it. So the idea for this regression problem is you'd want to predict this value. And you can see that it represents different stores. So you have different items in different stores, and you want to predict the outlet sale. So you have an item identifier, the weight, whether it's low or regular fat. You have the type, the categories, etc., etc. And you can use all these columns to predict what this value here is, and that's kind of the idea of regression. So the first step to this is if we want to define the Y column, so we want to make sure that we split this column out from the independent variables, because it's dependent variables. So the way we do that is we can just assign the name here, ycol equals so now we have the Y column. We're going to use a command called drop. So what this will do is we'll drop that column out from the data. So we define the X and Y data frame as data.drop. And what we want to drop is the Y column, because this will give us the X data, and this is basically it's training data. But before we do that, we have to change the axis so it drops out, because if you don't put axis equals 1, it will look index wise, whereas we want to drop column wise. So if we now do data drop, we can define, we now have the X, and this is the data that it trains on and compares to the dependent variable. Now, if you look here, we have the item identifier and the outlet identifier. Now, this we actually want to remove because it's a unique key for every single row. So basically what would happen is if you were to put this into categorical form, it would basically be one data point for each of these, and it's just a unique key. So you don't really want to pass this in the X data because it'd be useless. So we can either drop them out using the drop command, or what we can also do is use a command called set index on the data frame. So if I go back to this command, I do .set index. And we type in item. Right, and we do that, and then look back. You can now see that it's defined it as the index. So it's it's out of the actual data, it's just the index, so it won't be passed for training, which is good. And so let's rerun the drop of the Y column. So now we have now you have the X data, which is good. So I mentioned as well that we need to convert these to categorical form. So otherwise, if you pass that to any sort of machine learning algorithm as it stands, it wouldn't work. So we need to change that. So let's just define the categorical columns. So we can do that quickly here. So you just list them like so. Here. And we'll also do it for the numerical columns as well. Right, so now what we want to do is import the functions for the conversions. So if we do from sklearn pre-processing, I'll see what I'm doing here first. And import one coder here. So now we've imported the one hot encoder class, which is what you need for the next step. So I showed in the slides, it follows the convention of you assigning it to a variable like so. So let's call it enc. And then let's do one hot encoder. Right. So now you have the class defined here as this object. And as I mentioned, it follows the convention where you do fit transform. So if you do enc dot fit transform, then you pass it the X data, and if you do this, it'll make sure it only passes the X data with the categorical columns. I'll show you first. So here we have the X data frame, but if you wanted to slice it on a certain amount of columns, if you do X bracket, sorry, categorical like this, which is this list here, it'll cut out all the other stuff and you just have the categorical columns left here. So that's what we're passing here. So if we do this dot fit transform, it creates it in the form that we want, which is what I showed you in the slides. Now, I did mention about training and testing that quite often you have that in all in one script. So I mentioned that you normally break away a bit of data to test on to make sure that it works correctly, which is a step we haven't done. So we need another command to this to break away a small snippet of the data to test on later. So if we use the command from sklearn dot module selection import train test split, and we run that, you now have a means of splitting the data with this function. So what we're going to do is if we define it as X test equals train split. And then if we pass the X and Y data frames, and let's choose the size we want to split by. So if we use the argument test size equals, and you do this a fraction, 1 being everything, 0 being nothing. So we do a fifth, let's say, and then we can also add a random state, which basically means it fixes a certain random state. So it's for basically recreation purposes. But if you weren't to add that, it would split it randomly by a fifth every time. Oh, Y is not defined. Missed a step. We need to define Y as well. So we defined X, we need to define Y. So Y equals data. Sorry. So I mentioned you can use the brackets to slice on the columns. So we're also going to do dot values. So now if we do this, we now have the Y column. So if I'm the dot values basically just removes it. It changes it from a data frame to a NumPy array. So just so you can see the difference, if I wasn't to do dot values, it would have all these values here, but it would be as a Pandas data frame. Whereas if I do dot values, it has it in this array. So going back to what we were doing before, so we want to split the test and training data. So let's do that. So now we have the test and training data. So the test data is a fifth of the size of the training data, and that's what we're going to keep to check how well the model does. So if we run this command again for converting to categorical form, we now want to do it on the training data. So right, and let's just assign that to a variable. So cat. Now you have in categorical form, and let's also pass the numerical columns. We can do that like so. As you can see, these are now the numerical columns, and that's the categorical columns. So finally, we want to join them back together. So we can do that with this function. And this is where NumPy comes in. As I said, it goes hand in hand with Pandas. We do this. We now have a set of data in the format that we want that the machine learning algorithm will understand. So we're almost there. We're almost ready to do some linear regression. So we just need to import the library. So from that command. So now we have the linear regression class imported, and we want to assign it to a variable like we did before. for the one hot encoder, so we can do it like so. So now we have the object, and this will contain all you need to do the linear regression using the logic that described in the slides earlier. So the step next is we want to train the model, and we use that as model.fit. And we just passed the training data and the Y column, which is also with the training data. If we press enter, so you can see here where NaN values cause problems. There are some algorithms that can handle NaN values, but quite often they don't. So this is what I mean when you have to look at the data first, because what we've done actually is we have just jumped straight to the training section, and we haven't even looked at the data. So if we go back to what we did, we're going to have to find a way of processing the NaN values. So we can use the command that I said earlier, fill NA, or we can use drop NA. So if we go to the data here, have a look, there are NaN values in here somewhere. So look, you can see them here. So if we use data.drop NA, it will now remove the entries where there's NaN values. So if we run this again, then we do model.fit. It now works, and it's now trained the model. But now we want to see how well it performs. So if we go back to, we want to find out what the score is. So if we use this command, model.score, and we put the X test, Y test, and now we're passing the test data in. Oh, sorry, I missed a step. Meant to do the training first. So that's the R² score, and the R² score goes between 1 and 0. And ideally, I would say you'd want to be minimum at 0.6 for regression. Even better than that would be 0.8, 0.9. So this is quite a low score, and that's on the training data. So I mentioned that we want to really score it on the test data, because quite often, I'll show it here, if I print the score of the training data, it will be higher than the score on the test data, and that's quite often the case. So it's very important that you check the score on the test data and not the trained data. So if we do what we did here only for the test data, and so if we take these bits, put them here, you've already done the fit part, so you can probably just transform. You don't have to do fit you don't have to fit a second time. Same data, do X test. And stack it together. So if we do this, you now have the test snippet you're going to test the model on. So if we do that again, we do model.score x test y test. You see it's a different value to the training score, and in fact this one's slightly higher. So if we print that out as well, let's move this. So you can see, yeah, the training score is different to the test score, and it's the test score that we want to look at. So you can see this is actually quite a low value. So this is where data cleaning comes in, because we want to ideally make that better. So how do we do it? So let's actually look at the data. So previously when we read it in, what we did is we dropped all the NaN entries, but quite often you'll find with machine learning algorithms or models, they work much better if you actually keep these values in and you replace them with something else. It kind of props them up, and I'll show you what I mean. So if we do a loop, so if we do a for loop, so for C so yeah, for C and x C equals x C, and if we want to basically fill the blank entries with a new entry. So before in the demo I did mode, so or at mean. So let's use mode because this is text. So what this will do is for every time that it comes across a blank entry, it will replace it with the mode in that column, so the most occurrences of that. So if we run this, so and go back to the X data, before where there was blank entries, they're now not. They have the mode in them, and we can do the same for numerical values as well. We'll see in. Now there's much smarter ways to do this than what I'm doing here. This is just to demonstrate the difference between dropping out whole rows of data versus replacing them with things like the mean. And this is called imputation. So now if we look at that, we don't have any blank entries. So if we were to do x dot drop NA, sorry, my mistake. Take that out and run this command again and go through those. So we run these and do x dot drop NA. Yeah, you can see previously there was about 4,000 rows because it removed about half of them, and now there's more like 8,000 rows of data, which you'll see dramatically improves the score. But we should also look at some of the other columns. So we can also look at what populates the categorical columns. So for this, if you do another loop and you do for C in capitals, font C xc dot unique. You can see for every column there's this unique command basically makes a list of all the different values that are in them, all the unique values. So if we look at them here, you can see here, for example, the in fat content it has low fat, regular, low fat and lowercase, LF and reg. Really, all you really want are these two, because low fat is basically low fat, and LF are basically this, and the same for reg. So that's one part of cleaning what we should do. So as I showed in this tutorial before, if we take the item column, fat content, and we do dot replace, we pass these values in, it will replace all the times that you get low fat or LF with low fat. But we can also do dot replace again for reg, replace it with regular. So now if we run this and do dot unique, you can see there's only 2 entries there in that array. So that's a bit of cleaning which will help improve things. So if we now assign that to that column, so to make it permanent, ooh, there we go. So now that we've done a bit of cleaning, we should expect to get a better score. So let's just put this in and put the for loops in as well. Right, so now we've done a bit of cleaning. Let's rerun this section again and see how it performs now that we've cleaned it a bit. Sorry, done something here. It's because we haven't fitted the model. We need to put model.fit. For train data and model.fit for test data. Oh, sorry, for the test data. Let's run that again. Now you can see the score is higher now. So as before, it was 0.4 now, and it's now jumped up to 5.57, and that's through cleaning. So it's very important that you clean the data and look at it before you do any of the actual training. And you can see the actual training the model takes seconds. It's the cleaning step which is the important step. So this has been very brief run through of how to train data, clean it. But in theory, you can now have a model that can predict the the value of an item for any outlet in a shop using that data, which is pretty cool. So that's regression. I'm going to very quickly talk about classification, since it's another powerful tool of machine learning. So let's go back to the slides. So with classification, this is where you want to put something into a class. So the class could be difference. I was citing moths and butterflies. If you have certain data with certain characteristics in the column, maybe you'll class it as a butterfly or a moth, for example. And that's what classification is. And the algorithm we're going to look at is support vector machines. You can actually do regression with this logic as well, but we're going to look at classification. So let's look at this here. So you can see here there's a difference between this data. So this is in 2D, and you can see these data points here are I've given them the negatives, but they're just data points, and these ones are positive, and they basically represent two different classes. So this, for example, it could be oranges and apples. Say this side is oranges and this side is apples, and this could be the X and Y could be the color spectrum. So you could go through color spectrum. When it goes from green to orange, that means oranges, and vice versa. So there's a distinct difference between this data. So what we want to do is find a point. We want to find a way of splitting it. So what we can do is we can use support vector machines to do that. So what they do is they find a line through the middle, but it's not just a line. If I run through this, they almost find a path. So if you imagine this is a road, and it searches through and it finds the point where the road is at its maximum. So it starts with a line, and then it finds the maximum road. Now, what the road represents is where the end point, the end bits of the road lie on the data points, and these data points are actually the support vectors themselves. So they are basically the influence of what is classified as what. So these points here don't govern the classification. It's actually these points. And you're trying to maximize the distance here between this line. And that's how the algorithm works. I'm not going to go into the detail of maths like I did with regression, because you could spend a whole session talking about that. And I'm just going to quickly go through how it works. So once it iterates through and it finds this distance here, you now have a way of splitting the two classes like so. Now, the reason I wanted to talk about support vector machines is not because of they're very powerful in the sense that this is quite a simple split with a line. It works. You could probably use other methods to do this, but let's take an example when you have this relationship. This isn't easy to split data with just a line. If you try to split these data points with a line, it wouldn't work. It's clearly non-linear splitting. But if you did this, you could definitely split the data. And this is where support vector machines come in handy, especially for classification. Okay, I said I wouldn't talk about the maths. I will do a little bit, because this is where I'm going to explain something called the kernel trick. Now, support vector machines, they have this very nifty trick where they are able to split data like this through doing a transformation. So they basically run the algorithm gets a mathematical expression which uses it in Lagrangian form, and then it basically tries to maximize that distance using some sort of solver, so something like quadratic programming, which I won't go into here. But they do a certain jigging of the maths to basically make sure that the optimization or the minimization is just based on the dot product of the samples, which are here. So the reason they want to do that is because you can do a transformation on that data. So this is what the kernel trick really is. So you do some sort of transformation where you convert these data points, you basically add a dimension. So there's different sort of kernels that you can use to do this. So quite often they use a Gaussian kernel, which I'm going to show in this example, but you can also have polynomials where if you imagine this is 2D, and I'll show you what I mean. In 3D, if you were to add these transformations to this data, you can then make it go outwards in the Z direction, and then you can put what was a line, it's now a hyperplane through this to get this circular splitting here. So if I show you what I mean, that's that data. It's done this transformation to the data, and now you can put a splitting once it's there, just here. Now, the beauty of this is that it's unlike, because you do a transformation just on this part of the expressions, you don't, it simplifies things a lot, because you are doing a transformation, but only on the actual dot product here. Whereas if you didn't have it like this, you'd have to have a lot more complex mathematics, and it would be a lot more complicated to solve. So it basically simplifies things and makes these sort of splits very easy to do, and it's very fast. So that's support vector machines. So they are very powerful. They've been around a while. So I think it was the 60s where the idea first came about, but I think it was the 90s when they first started using them, because that's when computer power was good enough to actually explore them. So they have advantages that they're very good at finding a solution, and they're not affected by a local minima compared to neural networks. In fact, they're quite a good alternative to neural networks quite a lot. They're less prone to overfitting, which I haven't really talked about in this, but overfitting is basically when you shape the model so much to the training data that it's so fitted to the training data that when you give it the test data, it performs very badly, and that's overfitting. And it's also a good, as I mentioned, a good alternative to neural networks. So that means it can perform well with unstructured data. So for things like images and stuff. One of the issues with it is it takes large computational time, especially when you have large data set and many features. So on small data sets, it works really well, but the larger you get, it gets slow quite quickly. And also, unlike with the linear regression, it's not very interpretable. So it's sort of more of a black box. With linear regression, you can see what the coefficients are, and you can see which coefficients govern the shape more than others, whereas you can't really see what's happened inside the algorithm itself with this, and that's what it means by interpretable. So before I leave you, I might do one last tutorial on classification so you can see how it works. So let me clear all this again. Sorry. Let's restart. Right, so let's import libraries, and then let's also set the options. So the file name that I'm looking at is loan predict. Let's check we're in the right path. Yes, so let's put that here. So I'm going to run through this a bit quicker than last time. So let's just pass the data with the command before, and I'll just quickly show you what's in it. So this is the Y column. This is the loan predictor data. So this is basically information about a certain customer for a bank, say, and then you have on this side whether they're likely to get a loan or not. So yes is based on this information, they got a loan, and no, they didn't. So what we want to do is find the way of predicting just based on these characteristics or this information, whether they got a loan or not. And that's classification. So if we do similar to what we did before, so we define the Y column. And X equals data dot Y one. Values. Oops. Going to define the numerical and categorical columns like so. And then we're going to start looking at classification. So I mentioned previously about scaling. So this is actually one of the algorithms which works much better if you scale the data. If I have time, I'll show you the difference between scaling and not scaling. It's basically to do with shows you the analogy of the road. It's to do with the splitting of that. You need to scale it, so it's roughly, we're dealing with units of one. So that's why if we bring in the library for scaling, we can make this perform better. So oops. So the library we want to import is standard scalar. And this is the library that we use for, or the function, sorry, not the library that we use for scaling. So as we did before, we define, we pass these functions or these classes to variables to initialize them as objects. So we do that. And then we want to, as we did before, split the data into the test and training set like so. Oops, we need to import the routine for splitting the data. Let's do that again. Then you also want to rearrange this so that, as we did before, so that we have the training data in the correct format. Let's do this. So for classification for support vector machines, you use from sklearn.svm import svc. You can use this method for regression called svr, but we're doing classification, so use svc. So model equals svc. You initialize it like so, and do the model.fit train y train. See, we need to make sure we do something about the blank entries. So for this, I'm just going to very quickly just drop them and run through the step again. There we go. So we fitted the data to the algorithm. Right, so now we fitted the data, we'll print the training score, but really what we want to do is look at the test score. So very quickly, that's the score for the training data, but really we want to look at the test data. So if we repeat what we did for the test data, like so, and then print the score like so. There you have it. So that's the score of the classification model. And this score, it's no longer R squared. This score is the accuracy metric. There are loads of others, but this is just the default one for this SVC model. So I know I rushed through very quickly with this, and of course you can do loads of steps to clean the data and make sure it performs well. The data sets I've used are sort of pre-processed, and basically they've been tweaked to make sure that it's for demo purposes. But quite often, as I mentioned, you would have to spend the majority of your time making sure that data is in the correct format and stuff. So I realized that this was, let's go back to the presentation. So I realized I've run through everything very quickly. So we've gone through the whole process of training, examining, converting, and testing. And that, in theory, should give you the ability to do very basic machine learning. But there are many different steps you can do, and this is just an introduction. There's all sorts, there's all different types of scoring and stuff. There's different types of models, but I hope this has given you enough to give you a starting point to really get to grips with machine learning. And I hope that a lot of the modules will go into more detail about the different aspects of it, etc. But I hope the overview of everything was useful. And yeah, thanks for listening.